Okay, so let's give you a brief review for previous class. In the previous class, we show you how to deal with a system being applied with two or more driving forces and how these driving forces affect the different types of flux. In this section, we interpret and explain what's the coupling coefficient, right? And in order to explain this, we use the continuity equation of entropy that states that the entropy change the change of entropy of the system can be equals to the change of entropy from surroundings. We call it a flux, entropy flux from surrounding, and also plus the changes of entropy produced by these systems. So this we call it as a continuity equation of entropy. So by partial t to this equation, so we got partial t and also partial valent, per unit valent, then you can get the entropy partial s partial t equals to the entropy production rate per valent, then the flux turn when you take partial with t, partial s flux partial t, then what you get would be the minus divergence of entropy flux. So this is we call a continuity equation of entropy. So when you are interested in the entropy change of your system or your materials, so that will be summed up by the entropy production rate produced by the system, and also the entropy changes from surroundings. So after simply just move this term to the left, then we can get this equation. And combined with the energy conservation law based on the lecture note, we show lecture note on page 6 to 7, then we can get these beautiful equations linking the entropy production rate of the system with various kind of driving force applied on the system, and also the corresponding flux. So when there exist two or more driving force, you just need to sum this flux and force terms up together. So for example, that if now we have a metal bar and there are two driving force, which is the temperature gradient and also the electric field applied on the system, and what's the entropy production rate. So there are two driving forces, right? So based on this equation, we can write down like absolute temperature times the entropy production rate per valent would be equals to the current density times the driving force is the F small q plus the heat flux times the corresponding driving force, which is the temperature gradient, F capital Q. But as we know, there's a relationship between the flux and force, right? When there exist two or more driving force, each type or each kinds of driving force will drive the flux of entities. So this means the current density is not only driven by what? Not only driven by the electrical field, we're also driven by the temperature gradient. So you can write this relationship here. So we can, as long as you put the direct and coupling coefficient and also plug in and put in the driving force term, then you can get the flux, the current density here. And the same concept can be applied on the heat flow. Heat flow here in the system is not only be driven by the F capital Q, the temperature gradient term, and also be driven by the electrical field. Okay, so as long as you got the heat flux and current density then you can just put in here, then and also times the FQ and times the F capital Q, then sum these two terms up, then you can get the entropy production rate per volume. This is how we deal with the system being applied with two driving forces. Okay. And actually, it's the same concept, right? If you have the third driving force, you can just plug, just end this extra term here, and you also will have the other. For example, if that is the atomic flux, right? Then the atomic flux will be driven by temperature gradient, electric field, and also the chemical potential gradient. And because if there's a three driving force, so you need to end it extra term here, right? And the extra term here will be the chemical potential gradient will also affect the heat flow, and plus the extra term is the chemical potential gradient also will affect the current density. So will be something like that. So depends on how many driving forces are being applied on this system. Okay, so you can calculate the entropy production rate. And in this slide, actually, we just show you are there any way to help us to measure the heat flux, atomic flux, and the current density. And people usually, or scientists usually use the Fourier law to measure the heat flux. So when you not measure the heat flux, measure the thermoconductivity related to this heat flux. Like, for example, like you measure the heat flux divided by temperature gradient being applied on the system, then you got the kappa thermoconductivity. The same thing is like if you want to know the mobility of these materials, then you will measure the atomic flux divided by concentration and also divided by chemical potential gradient. Then you can get the mobility of this atom. The mobility actually is the moving velocity of moving atom, right, in your materials. Okay, so people usually will how to get the electrical conductivity. So usually you will measure the current density divided by electrical field. So normally it's like that, right? You have a metal, your material, you apply an electrical field on this material, then you will measure the current, how much current goes through this material. So you just simply divided the current divided by the electrical field you apply, then you got the electrical conductivity. So that's how people measure the intrinsic material property, such as thermoconductivity, mobility, and electrical conductivity of your interesting materials. Okay, so next, just hope you have some idea. Yes, you got this beautiful relationship, and you also know the flux and force. There's a beautiful relationship between the flux and force equation, and in between actually is the coefficient. We call it the direct or coupling coefficient. For direct coefficient, actually is directed by the corresponding driving force, and coupling means like is other type of driving force will also driven a specific flux of entities. So, but that's not a major effect. So some people call it a coupling term. So no matter it's a direct or coupling coefficient, this coefficient actually is directly related to some kind of intrinsic material properties. So this will be every material system or every material has its own direct coupling coefficient. And what are they? So what are this direct coefficient? L capital Q, and what is the L capital Q, and what is the L small q? So we are going to use some examples to demonstrate what's the relationship between the direct coefficient with some intrinsic material property. So for the first example, be a thermoconductivity kappa. Kappa is equals to L capital Q divided by T, and measure under no electrical field. I'll measure under the condition with no electrical field and no concentration gradient. And electrical conductivity, low, is equals to L small q. Or you can say L small q is equals to low electrical conductivity and must be measured under isothermal conditions. So in previous slide, we demonstrate that when the system only have one driving force, which is the temperature gradient, then you can get that the thermal conductivity actually is equals to L capital Q divided by T. But however, if we added the extra driving force on the system, which we call is electrical field, right? But this electrical field did not cause any current goes through these materials. So yes, we do have two driving force. But after two driving force, but there's no electric current went through these materials, right? So you got a relationship between these two, right? So let's tell you what? Let's tell you that for the current density goes to 0, but you can have some idea that yes, there still exists a temperature gradient and also the electrical field, but however, this some kind of cancel. This effect are cancelled, so that would result in there's no current density went through your materials, right? And for this system, for heat flow, yes, the temperature gradient is not the only factor to driven the heat flow. The electrical field also contributes some amount of heat flux, and you can measure the heat flux. But don't forget that the heat flux you measured is the combination effect of these two driving forces. So if you usually we can measure the heat flux, right? And if we directly using the Fourier's law, we directly divided by the minus temperature gradient, and we got the value of kappa prime, and this value would be not the kappa it will be the kappa minus extra term. So you are going to underestimate your thermal conductivity because there's the other driving force exists in your system. So the heat flux you measure is the combination effect contribute from the heat flux, the F capital Q and F small q. Okay, so the same thing happened on the electrical flow cases. The cases states that now we have a metal connect to the battery, and if we measure the electrical conductivity under isothermal conditions, then we demonstrate that electrical conductivity is equals to L small q, right? So in this case, if you look carefully for these equations, you will have some idea that yes, the heat flux, because there are two possible driving force apply on this system, and for the temperature gradient, because it's isothermal conditions, so we can drop this term out. So in this case, there's only one factor driving force to drive the heat flux, which is the battery, the electrical field. The battery you connected to this material, or the electrical field you apply on this system. So even in this system, the temperature gradient is equals to 0, but let's still have some heat flux flow through your materials. This is a different concept, right? Sometimes people will say, oh, there's no temperature gradient, so there's no heat flux. This concept is not true. Based on this, even as long as it exists a driving force, there must be the corresponding flux. And for example, this is current density, right? Because there's no temperature gradient, so only exists the electrical field or battery. connect to these materials. So the driving force here is the electrical field we apply, right? So based on this, the current density we measure is the correct current density, because only directly contribute from the electrical field we apply on this system. There's no other driving force exist or apply on this system. So based on the Ohm's law, we can measure the correct or accurate electrical conductivity though, and this will be equals to L small q. But however, if we change the boundary condition to the diabatic condition, in this case it states that the JQ heat flux equals to 0. So based on this, you get a relationship between the F capital Q and F small q. Then you substitute this in this relationship, then we can know in this condition, in a diabatic condition, when I measure the current density, how much current density went through these materials, and directly divided by the electrical field I apply on the system, and I will get a low prong, right? This low prong is not exactly the low, it's difference. It equals to low minus an extra term, and this term is why we have this term, because in this system there's to exist the other driving force. So this driving force will contribute extra heat flux, so that will cause you have that will cause the that will interference, or that will disturb you to get the correct to measure the correct electrical conductivity. Okay. So give you some comment, something like that. If you want to measure the correct electrical conductivity of your materials, you need to assure that there's only direct driving force applied on your materials. There's no other types or forms of driving force exist in your systems. Because as long as there are some other types or kinds of driving force that must contribute some flux on the flux, your interesting flux, for example, like this, is a current density. Okay, so I give you some extra examples here. For previous slide, we just we put more efforts on like Entropy, or states that how important to get the accurate intrinsic material property, and what's the relationship between the kappa and L capital Q. What's the kappa and L capital Q, and what's the L small q actually is electrical conductivity, right? But we did to describe quantitatively describe the kinetics process. People always ask about entropy production rate. So for this case, actually is now we have the case we mentioned in Q1 is like we have a material, then we apply a temperature gradient on it. We only have there's only one driving force applied on this system. Can you just simply calculate the entropy production rate? So based on this equation, because there's only one driving force, so we just directly simply times the J capital Q, F capital Q together. Then we can, so this is a J capital Q, this is F capital Q. Then we can get the entropy production rate. So what's the J capital Q? Based on the Fourier's law, is a minus kappa temperature gradient. And this time you just copy it. So the result is like a kappa gradient T square, and it divided by T. And if you divided this T here, then you can directly get the entropy production rate per volume, right? So this is how we describe this thermal flow process. in our materials. And the other case is if we have the same thing as we have a metal bar, and there's a concentration gradient along this metal bar, and because there's a concentration gradient, so that means the atomic fraction of the atom is also varied with the varied along this material, right? The concentration gradient. So in order to do that, so all concentration gradient that implying that there's definitely a chemical potential gradient, right, along these materials. So if we just simply want to know this diffusion process, what's the corresponding entropy production rate, you just sum up the flux and driving force here. But the driving force here is just the chemical potential gradient caused by the concentration gradient, right? Okay, so you can just atomic flux times the minus temperature gradient, because this is a driving force for the mass diffusion, mass transport, right? So the atomic flux based on the fixed law will be minus mobility concentration and the driving force, which is a minus chemical potential gradient. So after simply just calculate that, you can get this, and if you divide it by T, then you got what? Entropy production rate per volume. So that's how we describe the heat flow process and mass diffusion or diffusion in solids by the entropy production rate per volume. Okay. So next we are going to move to the other two intrinsic material property. The first one is we call the Seebeck coefficient, and the second one is the Peltier coefficient. What is the Seebeck coefficient? As we mentioned, if you have a material, you apply the unit temperature gradient, and you apply a temperature gradient or temperature difference along your materials, then how much electrical field and electrical potential be generated from this material? We call this would be the Seebeck coefficient of this material. So if this material have higher Seebeck coefficient, that show you that what? When I apply the same amount of temperature gradient on these materials, and the one with higher Seebeck coefficient can generate higher electrical potential, right? And also will generate higher current. So that is the physical meaning for the Seebeck coefficient. And what's the Peltier coefficient? What is the Peltier coefficient? What the Peltier coefficient actually is some kind of complementary effect of Seebeck coefficient. This one we provide the temperature gradient or temperature difference along these materials. But in this case, and we generate the current, right? In this case, we supply or apply the current, then that will generate the temperature gradient. So that's some kind of complementary effect. And because these properties is also the intrinsic material property, so you need to measure that under specific boundary condition. Then you can get the accurate or correct Seebeck coefficient of this material. So for Seebeck coefficient, you need to measure that in the open circuit, and for Peltier coefficient, you need to measure that in the isothermal condition. So we will explain this in the following slide. Just hope you have some idea about these two effects. So let's move to the Seebeck effect. So what's a Seebeck effect? It's been discovered by 1822. Around like 200 years old. Thomas John Seebeck find that interesting stuff is when he combined the copper and the bismuth together and just heated one junction up. So just heat it up to create a temperature gradient or temperature difference between these two junctions, then interesting things happen. He found that the magnetic needle would be deflected. So he will think about, oh, what happened here? So in the beginning, probably because something caused the magnetic deflected, right? Is that the temperature gradient or temperature difference? But when he did more experiments, he found that the magnitude of this deflection varied with the type of conducting materials you choose, and also the temperature grade difference between two junctions. But that doesn't depending on the temperature distribution along these conductors. So nothing related to the temperature distribution along these materials, but it affects what kind of materials you choose and also the temperature difference between these two junctions. So he found what? He found that there's a thermal and magnetic effect. Thermal difference, so the story, after serious investigation, he found the story would be like that. There's a thermal difference will cause the current, and this current will generate the magnetic field that will cause the needle be deflected. So the degree or magnitude of the deflection depending on how much current be generated. So this effect actually is a thermal electrical effect, because thermal difference causes the electrical current difference. So we call it thermal electric effect. So you can interpret as this effect is a relationship between the F capital Q is a thermal driving force. How much when I apply the unit thermal driving force? If I apply a unit thermal driving force, how much current I can generate? So this is the physical meaning of what? L small q capital Q, right? This indirect coupling coefficient, or you say coupling coefficient, because the driving force is the F capital Q. When I apply a unit F capital Q, how much current I will be generate, right? Okay, so based on this concept, you know that every materials have its own Seebeck coefficient. So how to measure that? Based on the definition, actually the Seebeck coefficient defined by when I apply a temperature difference at two ends, then how much electrical potential be generated. So usually people will put your materials here and would heat it one side up by heater and cool one side down as a cooler, so to create a temperature difference at these two junctions, and that will use the potentiometer to measure the electrical potential difference on these two ends, across these two ends. So this we define as a Seebeck coefficient. So each material you have its own Seebeck coefficient, okay? But usually most of materials, the Seebeck coefficient of most materials is quite low, especially for the metal is quite low. So some people ask about this kind of material. What kind of material can generate more electrical potential under the constant temperature difference? I would say let's classify materials we call the thermoelectrical materials. And how to evaluate whether this material is thermoelectric materials or not? We call it a ZT, the value of ZT. Z is equals to Seebeck coefficient square of Seebeck coefficient, though is electrical conductivity, and divided by kappa. So if this value is higher, that means this material is suitable, is electrical is a thermoelectrical materials. So this kind of material must have what? If you want Z is get larger and larger, then you need to have a large value of Seebeck coefficient, large value of electrical conductivity, but small thermoconductivity. There's some conflicts, right? Higher electrical conductivity, but smaller thermoconductivity. For example, like a metal have a higher electrical conductivity, but also higher thermoconductivity. So metal is not suitable for, it's not a kind of thermoelectrical materials, because for metal, if you got a higher electrical conductivity, usually it will accompany with larger thermoconductivity, right? Okay, so some people probably would ask why need the material with a smaller thermoconductivity. If you have a small thermoconductivity, then you can maintain what? You can maintain the temperature difference along your materials. Because this thermoelectrical materials, the application for that is what? When I apply a temperature gradient, then you can generate the electrical potential, right? But if your material is highly thermoconductive materials, when I generate the temperature, it's very difficult to generate a temperature difference along these materials, right? Because the thermoconductivity is too good. So it's very difficult to generate the temperature difference across your materials. So that's why in this so the thermoconductivity must be smaller in this kind of thermoelectrical applications. Okay, so let's move to the famous applications for Seebeck effect is the one you always used in your lab, is we call a thermocouple. So if you take a look on this diagram, I mean these pictures, I just simplify this structure, this pair of material into a simplified circuit. We have one, and this actually is a typical schematic for thermocouple. So we have one A material and B material. We have two material. Then and we make a junction here, and we connect this AB materials to the potentiometer. Then what? If there's a temperature difference between these two junctions, then I can measure that will cause the different electrical potential gradient, then measured by this potentiometer. So this is how the thermocouple works, because you always use a thermocouple to detect the unknown temperature, right? So as long as we know, we use the standard curve to calculate, calibration this thermocouple, then we can know the relationship between the electrical potential gradient, electrical potential versus the delta T, right? So we can, by using this concept, we can use this junction to detect the unknown temperature. So this is how the thermocouple works. So in order to demonstrate what's the Seebeck coefficient? So we use these figures to explain this. Because also, if you take a look on this one, yes, there's a driving force, temperature gradient exists on this system, right? And also we have a potentiometer, so then implying that there's an electrical field exists in this system. So we do have two driving force. So based on the flux force relationship or equation, you can write down this, right? The current density directly driven by the electrical field and indirectly driven by the heat flux. And also, this is, we know it is the open circuit. So open circuit implying that this current density will be equals to 0. So this relationship will be equals to 0. So we got because this equals to 0, so we just after arrangement we got the d phi over dt at the open circuit can be expressed like this. It's related to by the coupling coefficient divided by direct coefficient times t. Okay, so in order to get the potential measure at terminal 1 and terminal 2, so we are going to use this equation. Just move the dt to the right-hand side and take the integral for both sides. So the integral from where to where for the potential phi part, we just from integral from junction to 1. And for the temperature part will be the T delta T integral to T. Okay, so we take the integral, so we take the junction part to the 1 and also the junction part to the 2 for the material B. So take this integral, we got the phi 1 minus phi j, right? And if you take the integral dt, move here, right, and take the integral, we just want to, and this is the coupling and direct coefficient, and we label with, that means that this is belongs to a material, because also you know, every material have its own direct and coupling coefficient. So we need to label all this belongs to material A, and the integral region is t plus delta t to t, and dt. Okay, so minus, and if you take the integral dt divided by t, it will be the log t, right? And minus, so log t minus, so it will be log t minus log t plus delta t, and minus, so you just simply will get the log 1 plus delta t over t. And because if we assume delta t over t is very small, then based on this approximation, log 1 plus x, and if x is quite small, then we can approach to x, so we can do this kind of x, so left x here. So the same thing the same thing be performed on material B. Then in order to get the potential difference, the potential we measure by the potentiometer, so we just need to use this term to minus this term, right? Then we can drop the phi j. Okay, so phi AB is phi 1 minus phi 2. Then this one minus this one, and we take the delta t over t out, and this belongs to A material, this belongs to B material. So we know the phi AB, the electrical potential we measure by the potentiometer, can be expressed like this. So what's the Seebeck coefficient? Is the temperature difference along two junctions is a delta T. We apply this temperature difference on these two junctions, and how much phi AB I can generate. So this we call a Seebeck coefficient. But here we have two material, right? So this is SAB is A relative to B. So if you grab this phi AB here and divided by T, then you got this relationship, right? And this SAB actually just tell you this SA relative to B, so SA minus SB. So based on this relationship, you can get what? The coupling coefficient L small q capital Q equals to what? T L small q S T L small q S. And L small q as we know is equals to rho, so it will be T as rho. So now we successfully get the intrinsic material property of this coupling coefficient L small q capital Q is equals to absolute temperature times the Seebeck coefficient of this material times the electrical conductivity of this material. So we can get this. And this coupling coefficient is will vary by temperature, Seebeck coefficient, also the electrical conductivity. Okay, but in this case, it's open circuit, so we get this result, right? So in order to measure the correct Seebeck coefficient of your materials, you need to measure that under the condition with open circuit. And also Seebeck coefficient, based on series calculation, we know it is Seebeck coefficient times the rho T equals to this coupling coefficient. So now we got this coupling coefficient successfully. Okay.